Alright, silly people, here's the situation. We have a potential that's kind of just two finite square wells right next to each other. They both have length A and separation between them B. And we're going to talk about what the wave functions look like without doing any calculations, because Griffiths says no calculations in this one. So the first case is B equals 0, so there is no separation in between the finite square wells, so it's just one big finite square well. So we'll just draw the ground state and the first excited state wave functions for these. The ground state kind of having a Gaussian shape around x equals 0. So that's psi 1, and then the first excited state having a pattern that's like two Gaussians split down the middle, one going negative and then one going positive. So kind of like that. And that's psi 2. And that's cool. For the next thing, we have that B is approximately equal to A. The fact that they're approximately equal doesn't matter. It's just that there is like a degree of separation that's not negligible, like in between the boxes now. So we're going to have a sort of thing where it's going to try to be a Gaussian, like one hump of a Gaussian in the first excited state, but it's going to try and go towards 0 when it's hitting x equals 0. So it has to be like this, coming in here, going up, dying off a bit towards x equals 0, then going back up in the other well, and then dying off again. Sort of like that, right? That's psi 1. Psi 2 is going to do the same sort of thing, right? It's going to come in and try to be like psi 2 with no gap, but it has to die off towards the middle quite a bit. But then it's going to come in and do this sort of thing again and die off. That's psi 2. Finally, for B much greater than A, so the degree of separation between them is so great that psi 1 is going to basically become 0 in between the two wells. So we have here a Gaussian, and it's going to completely die off in the middle, and then another Gaussian. So it's just like having two unconnected finite square wells just in the same space. Same thing for psi 1 there. Same thing for psi 2. It's going to have this really well-defined behavior in the first square well, die off to 0 really quickly, and then go back up in the other well. So that's psi 2. The interesting thing is that in the positive x region, it kind of just looks like there's two finite square well ground states, and that's kind of interesting, and that's what we're going to use to surmise the shape of the energy graph as B increases, right? So for increasing B, so okay, in B equals 0, right, they're both starting at like the energy values for the finite square well. So I'm going to put E2 or E1 down here, and then E2 is quite a bit larger than E1. So I'm going to stick it right there, E2. And as we said, like if we increase separation, the energy value for psi 2 becomes pretty much equal to that of psi 1. So they're going to meet in the middle somewhere where the energy for E2 decreases by a little bit. because of the separation. So I'm going to draw a little dashed line here where they will meet in the middle. And then it's going to be an asymptotic behavior. So it's going to look like this, just kind of approaching the line but never really touching it asymptotically as it goes off into infinity. Same thing for E2. It's going to sort of becoming closer and closer asymptotically. Okay, so that's kind of the energy graph. The thing about the potential is that it is a rough estimate of how electron potentials work in atoms that are right next to each other, according to Griffiths. And so he asked, in light of what we found for the energy plot, how does the energy of the electrons affect atoms nearby to the atom in question? So the thing about multi-particle systems is that they're always trying to get to a state that has less energy, right? So you can see that E2 decreases as separation increases, and so you can guess that if you have electrons in the first excited state, that they are going to try and get to that lower energy state, so they have to push away the atoms. They have to increase the separation to get that nice value. But if you have ground state electrons, then the in the middle part is quite a bit higher than the ground state, like for the atoms being right next to each other. So if you have ground state electrons, they'll actually smush the two atoms together. And I think that's, in my understanding, that's kind of how ionic bonds work. You have ground state electrons that want to be filling up energy levels, and so it grabs other atoms towards it to fill those energy levels, and that's kind of decreasing the separation until it hits the barrier of proton neutron repulsion. And then for excited electrons, that's why whenever you try and touch an atom, it will always just push away the electrons, right? Your nuclei aren't going to touch, right? Okay.